So in the multiple choice example number 1, we're going to find the area that is bounded between y is equal to x squared minus 3, which is a parabola, and the line y is equal to 1, which is a horizontal line. Sketching the graph, we can see the area between the two curves. It's going to be the integral. The top function is y is equal to 1, minus the bottom function, which is x squared minus 3. We need to get to our interval, so we'll set our two equations equal to each other to find out where they intersect. X squared minus 3 is equal to 1. Solving will get x squared is equal to 4, and then x is equal to plus or minus 2. So our area will go from negative 2 to 2. Since our area is symmetrical, we can see the left half of the graph is symmetrical to the right half. We can double our integral from 0 to 2 of 1 minus the quantity x squared minus 3. Simplifying the integral to get negative 1 minus x squared plus 3 dx. And again, further simplifying to get 4 minus x squared dx, then anti-deriving and solving the problem to get our area. In our second problem, we're going to go ahead and find the area between the parabola x squared, y squared is equal to x, which is a sideways parabola, and the line x plus y is equal to 2. Solving for y, we can see that we'll be graphing negative x plus 2. The y-intercept at 2 and a negative slope. We can see the area between the two curves that we'll be looking for. We'll rotate our picture to be able to see the top function and the bottom function, where the parabola is the bottom function and the line will be the top function for the area between our two curves. Solving our line in terms of y to have x is equal to negative y plus 2. Set our two functions equal to each other. Y squared is equal to negative y plus 2. Y squared plus y minus 2 is equal to 0. Factoring to get y plus 2 times y minus 1 is equal to 0. Our intersections will occur at y is equal to negative 2 and y is equal to 1. So the area we'll be calculating will be going from negative 2 until 1 using those y values. Even though we've rotated our picture, we need to think of reading our picture backwards, looking at it as a reflection. So our area is going to be the integral from negative 2 to 1 of the top function, which is negative y plus 2, minus our bottom function, which is y squared, dy. Anti-deriving, we'll get negative 1/2 y squared plus 2y minus 1/3 y cubed from negative 2 to 1. Following our first fundamental theorem of calculus, replacing in 1, and then subtract replacing in negative 2. Then we'll simplify our problem and get our area. In our third problem, we're going to find the area between the curve y is equal to 2 over x and the line x plus y is equal to 3. Solving for y, we get y is equal to negative x plus 3. And we can see the area between the line and the curve, sketching that. To calculate our area, we'll do the integral from the line as the top function, which is negative x plus 3, minus the bottom function, which is the curve 2 over x. We need to get the intersection to find our interval, so we'll take 2 over x is equal to negative x plus 3. Multiplying both sides by x, we'll get 2 is equal to negative x squared plus 3x. Bringing over x squared and 3x to get x squared minus 3x plus 2 is equal to 0. Factoring to get x minus 2 times x minus 1. And our intersections are at x is equal to 2 and x is equal to 1. So our intersection at 2 and 1 will set up our interval for the integral from 1 to 2. We'll anti-derive to get negative 1/2 x squared plus 3x minus 2 natural log of the absolute value of x from 1 to 2. Replacing in our 2 and the 1, following that first fundamental theorem of calculus, and then simplify our problem to get the area. The area is underneath the sine curve and the cosine curve. So graphing both those functions above the x-axis, cosine intersects at pi over 2, and sine and cosine are the same when x is equal to pi over 4 in the first quadrant. So to set up the area, we're looking at the area from 0 to pi over 4 underneath the sine curve, plus the integral from the pi over 4 to pi over 2 underneath the cosine curve. An anti-deriving sine to get negative cosine from 0 to pi over 4. Anti-deriving cosine to get sine from pi over 4 to pi over 2. Then following the fundamental theorem of calculus, replacing in the values of pi over 4 and 0. And again, replacing in the value of pi over 2 and pi over 4. Simplifying to get negative radical 2 over 2 plus 1 minus radical 2 over 2, combining like terms. And then simplifying to get the answer of 2 minus radical 2. In our fifth problem, we're going to find the area bounded by y is equal to e to the x, y is equal to 1, y is equal to 2, and the vertical line x is equal to 3. You can see the area that we're shading in between is looking at a couple different functions. We have a top function up until some numbers from 0 to wherever e to the x is equal to 2. So we'll set e to the x is equal to 2. Taking the natural log of both sides, we'll have x is equal to the natural log of 2. So from 0 to the natural log of 2, we'll have the area underneath the curve e to the x, and above y is equal to 1. So our area from 0 to the natural log of 2 will be e to the x minus 1 dx. Then from the natural log of 2 until 3, we're looking for the area from 2 to 1. So we'll anti-derive e to the x to get e to the x and 1 to get minus x. From 0 to the natural log of 2. 2 minus 1 makes 1, so the antiderivative will be x from natural log of 2 till 3. Following our first fundamental theorem of calculus, we'll have e to the natural log of 2 minus natural log of 2 minus e to the 0 minus 0. For our second antiderivative, replacing in 3 and the natural log of 2. Simplifying our problem, we get 2 minus the natural log of 2. E to the 0 is 1, so we'll have minus 1 plus 3 natural log of 2. Simplifying 2 minus 1 plus 3, we'll get 4. And our natural log of 2's make minus 2 natural log of 2. And then our solution will be 4 minus natural log of 4.